Hello, this is Mr. Mac. This is the concept video on operations with radicals and simplifying radicals. Now, I'd like to start off with the properties of radicals that allow us to do the things that we do. The first one is the nth root of AB is the same thing as the nth root of A times the nth root of B. Now, what this means is that we can, if we're taking an nth root of a product, we can actually split the product up into its factors and take the nth root of each one and then multiply them together. Now, it's also true that the nth root of A over B is the same thing as the nth root of A over the nth root of B. So we can also split these up through division signs. We cannot, however, split them up through addition or subtraction signs. Now, with that being said, let's talk about operations with radicals. First of all, if we're going to multiply two radicals together, let's just take a look at something like this. The square root of 6x times the square root of 18xy squared. One of the things that we'll do is we'll go ahead and multiply them together. That would be the square root of 6 times 18 times x squared times y squared. Now, 6 times 18, I don't know what that is. Let's see. We got 48 and 6, 108. And then we have x squared, y squared. Now, at this particular point, then, what we want to do is we want to simplify this radical. Now, the first step, or the first thing that you need to think about when you're simplifying radicals is that no factor of the power of the index is allowed to be a factor of the radicand, okay? And in this particular case, this is square root, so there is an implied index of 2. So what we want to do is we want to take out all of the factors of 108 x squared y squared that are perfect squares. So we need to know what the perfect squares are. Well, it turns out in this case that the square root of 108 x squared y squared, 108 is 36 times 3. It turns out that 36 is the largest factor of 108 that's a perfect square. And then x squared is itself a perfect square, and y squared is a perfect square. So we would get, we can take the square root of 36, we get 6. We can take the square root of x squared, we get x. We can take the square root of y squared, we get y. And then we have the square root of 3 left inside. A couple of things that we do have to consider here. We have an even index here. We have an even, let's see, we have an even exponent on the y here, and we have an odd exponent on the y outside. So the y needs to be in absolute value signs. Now the x doesn't, because we don't have an even exponent on the x's in the original problem. So we don't need an absolute value on the x. The only time you need an absolute value, and I said this in the concept video last time, is if your index is even, if the exponent on the variable inside is even, and the exponent on the variable outside is odd. If that occurs, then you need to put absolute values around that particular factor. Now, the other thing that you might ask yourself is, Mr. McFarland, how did you know that 108's largest factor that was a perfect square was 36? Well, I just kind of recognized that. But if you don't know, there's a way to find that out. Now, what you do is you do a factor tree, and you break it down, you break the number down into its prime factors. See, 108 is, we can do 2 times 54. Now 2 is prime, so we'll keep working with 54. 54 is 2 times 27. 27, 3 times 9, and 9 is 3 times 3. So we have 2 times 2 times 3 times 3 times 3. Now, since our index is 2, what we're going to do is we're going to circle pairs of prime factors. We're going to circle prime factors in pairs of 2. And when we do that, we circle 2 2s and we circle 2 3s. Now, that's all the pairs we can get out of the prime factorization. If we then multiply everything that's circled, we will get the largest factor of 108 that's a perfect square. 2 times 2 is 4, times 3 is 12, times 3 is 36. That's where the 36 came from. And notice also that the product of everything not circled is the rest of what goes inside the radical. And then you can take the square root of the square part and so forth. So now, when you are simplifying radicals, any factor of the radicand that is a perfect power that's the same as the index needs to be brought out for the radical to be simplified. Let's take a look at a couple of examples of that. Here's one example, square root 75. Now the index is 2. When we don't write an index, it's implied to be 2. And notice that 75 has a factor of 25 that's a perfect square. It's 25 times 3. So we can take the square root of 25. It comes out as a 5. Now the 3 is not a perfect square, so it stays inside. And we end up with 5 radical 3. Now let's try something that has an index other than 2. How about the 4th root of 32? Now we're interested in the largest factor of 32 that's a perfect 4th, or in other words, that is something to the 4th power. And it turns out that 16 is that. Well, let's say you didn't recognize it right away. We've got, what, 4 times 8 is 32, and 4 is 2 times 2, and 8 is 2 times 4, and 4 is 2 times 2. Now, since we have an index of 4, we're going to circle like prime factors in groups of 4. So here's 4 2's circled together. And if you multiply all 4 of those 2's together, you get 16. That means 16 is the largest power of, or largest factor of 32 that's a perfect 4th power. Then we can take the 4th root of 16. It becomes 2. And then this 2 right here stays inside as 2, 4th root of 2. Now, be very careful. Don't lose this 4. Don't lose. Would that just be 1? Don't lose that 4. A lot of times students will start out with a 4th root and they'll end up with a square root. If you do that, there will be a price to pay. Don't lose that 4. All right. Now, the next thing in multiplying would be multiplying radicals that are, well, they're not alone. You might call them binomials. How about something like square root of 2 plus 3 times square root of 2 minus 5. Now, if you have these kind of irrational numbers and you want to multiply them together, notice they look like binomials and they are multiplied just as if they are binomials. You FOIL them. So first, square root of 2 times square root of 2 is 2. Now, yes, you could say the square root of 2 times the square root of 2 is 4, but realize that the square root of 2 is the number that when you multiply it by itself gives you 2. So when you're multiplying the square root of 2 by the square root of 2, you're multiplying it by itself. So you should see that it just is 2. Now, outer is negative 5 square root 2. Inner is positive 3 square root 2. And last is 3 times negative 5, negative 15. Now, one of the things I'd like to point out to you is that 2 and negative 15 are what we would consider like terms. And since we have the commutative and associative properties of addition, we can move things around and do 2 minus 15, we get negative 13. Now, the negative 5 square root 2 and the positive 3 square root 2, if that was negative 5x plus 3x, you'd have no trouble seeing that it was negative 2x. So the square root of 2 functions kind of like a variable here, even though we know what it is. So we get negative 2 square roots of 2. And so the answer would be negative 13 minus 2 square roots of 2. All right. Now, this brings us to another concept that needs to be taken care of right here, and that's the concept of conjugates. Now, we've already talked about complex conjugates. What we're going to talk about now is conjugates with radicals. If you have the binomial square root of 2 plus 3, for example, its conjugate is going to be square root 2 minus 3. If you have the square root of 2 minus 3, its conjugate is going to be square root of 2 plus 3. Now, the thing that makes these conjugates nice is when you multiply them together, the middle terms disappear. First, square root 2 times square root 2 is 2. Outer is negative 3 square root 2. Inner is positive 3 square root 2. And last is negative 9. So notice negative 3 square root 2 plus 3 square root 2 goes away, and we just get 2 minus 9, or negative 7. So when you have a binomial that contains a radical, if you can somehow figure out a way to multiply it by its conjugate, you can get an answer that doesn't have a radical in it, because the middle terms are where the radicals will reside, and in the conjugate idea, a plus b, a minus b, the middle term goes away. Now, let's go back to simplifying radicals. Once we've talked about the idea, we want no factor in an nth root that's a perfect nth power. Another thing that we require of a radical to be in simplest form is if it's a fraction, we do not want to allow in simplified form there to be any radicals in the denominator. Let's take a look at a couple of examples. 3 over the square root of 6, for example. This is not a radical in simplest form because we have a square root of 6 in the denominator. Now, the way we're going to handle this one is we're going to multiply by 1. Now, guys, it's very important that you understand that if we have something like 3 over the square root of 6, you can't just multiply willy-nilly by anything you want, because if you multiply it by, say, 5, you'll get something that's 5 times as large as the original thing. And if the answer is 3 square root of 6 and you have 5 times that much as your answer, that's the wrong answer. The only thing you're allowed to do when you're dealing with numbers and you want to simplify them is change the way they look but not their value. So to change the way they look but not their value, you can add 0 or multiply by 1. Now in this case, we're going to multiply by 1. Now the 1's going to look like this, square root 6 over square root 6. When you're multiplying fractions, the numerators get multiplied together, the denominators get multiplied together. The numerator is just 3 square root 6, and the denominator is the square root of 6 times the square root of 6. Now, if in your head first you said square root 36, that's okay, but I would like you to see that that's going to be 6. Now, this fraction is not completely reduced because there is a factor of 3 in the numerator and a factor of 3 in the denominator, so we end up with square root 6 over 2 as the radical in simplest form. Now, if you have a radical in the denominator and it's not a square root, let's take a look at an example of something like that. How about 12 over the 5th root of 4? Now, we do not want a radical in the denominator, and so we need to get rid of that. Now, here's the thing. If I take the nth root of a to the n, I'm going to get a. So what I want is I want as many factors of the radicand as the index. So first of all, I have to ask myself, what are the factors of the radicand? Well, this is 2 squared. So I have, if you look at this, inside the radical here, 2 factors of 2. But now the index tells me, the 5, tells me that I need 5 factors of 2 to be able to take the 5th root. So what I'm going to do is I want to multiply by 3 more factors of 2. Does everybody see that? Look at that carefully. See, I need 5 factors of 2. I have 2 factors of 2. So I'm going to multiply by 3 more factors of 2. And to get them inside, it also has to be in a 5th root. And so, once again, the only way to do this without changing the value is to also multiply the numerator by that. So I'm going to multiply the numerator by it as well. Now in the numerator, I get 12 times the 5th root of 8. And in the denominator, I get the 5th root of 2 to the 5th. Now that is 32, but it's easiest to just say the 5th root of 2 to the 5th, because then you should recognize the 5th root of 2 to the 5th as just 2, and we have 12 5th root 8 up here. Now notice there's a factor of 2 in this and a factor of 2 in this, so we'll cancel, and we end up with 6 times the 5th root of 8 as our radical in simplest form. Now, one other thing that could happen is we might have some fairly complicated looking radical like, how about if we do this, the 4th root of 2x over 3y squared, and we're wanting to simplify this. Now, this is the 4th root of 2x over the 4th root of 3y squared. What I like to do, though, is I like to just extend this, and we're going to multiply by 1 underneath the radical. Now, I have a 4th root. The index on this one is 4. So I need 4 factors of 3 in the denominator. I only have 1. So I need to multiply by 3 more factors of 3. Does everybody see that? To keep the value of the expression the same, I also need to multiply the numerator by 3 factors of 3. Now I have 2 factors of y in the denominator. I want 4, so I need to introduce 2 more factors of y in the denominator. I will also then put 2 factors of y in the numerator. Now this then becomes the 4th root of, 3 cubed is 27 times 2, 54 xy squared over 3 to the 4th y to the 4th. But now I can take the 4th root of 3 to the 4th, and I can take the 4th root of y to the 4th, and so I get the 4th root of 54 xy squared over 3y. One more check. In our original problem, we had an even index. We had an even exponent on the y inside, and we have an odd exponent on the y outside, so this y needs to be placed in absolute values. And that simplifies that. All right, now the next thing that we need to talk about is adding radicals. Sometimes you'll be asked to add radicals and it'll look like there's no possible way. How about square root 98 plus square root 18, let's do one more, plus square root, what shall we do, 50. Now, in fact, let's make this 2 square root 98. So each of these, what we're going to do first is we're going to simplify each of these radicals. Now, if you look at 98, do the factor tree, you'll find that 49 is the largest factor in of 98 that's a perfect square. So we have 2 times square root 49 times 2. Now 18, largest factor that's a perfect square is 9, and 50, largest factor that's a perfect square is 25. So we take the square root of 49, it is 7. We've got a 2 outside already, so 2 times 7 is 14, square root 2. We take the square root of 9, we get 3, square root 2. We take the square root of 25, we get 5, square root 2. Now we have 14 square roots of 2, plus 3 square roots of 2, that's 17 square roots of 2, plus 5 square roots of 2, that's 22 square roots of 2. Lots of 2's there. But anyway, and there we go. 22 square root of 2 is the answer to that original problem. So when you're adding radicals, you simplify the radicals. Now, let's just do one more here so that you'll kind of understand. Square root 147 plus square root 27 plus square root 8. Now, the largest factor of 147 that's a perfect square is 49, so we get square root 49 times 3. Largest factor of 27 that's a perfect square is 9, so we get square root 9 times 3. The largest factor of 8 that's a perfect square is 4, so we get square root 4 times 2. Now we can take the square root of 49, that's 7 square roots of 3. Take the square root of 9, that's 3 square roots of 3. Take the square root of 4, that's 2 square roots of 2. Now, these two terms are alike. We can add them together because that's 7 square roots of 3 plus 3 square roots of 3, which is 10 square roots of 3. But square roots of 3 and square roots of 2 don't combine to make 12 square roots of what? We don't know. We're adding there. So you cannot add those two terms because they are not alike. For radicals to be alike, they have to have the same index and the same radicand, and we don't have that in this particular case. So there's a lot more information for you as you view the solution videos, but that takes care of the concept of simplifying radicals and operating with radicals. Oh, no, there is one more thing. Let me continue here. If you have a fraction like, let's see, I did one here, didn't I? I guess I didn't write one down. Okay, let's just make one here. How about 15 over the square root of 7 plus the square root of 2? And we want to simplify this. Now, to do this, we need to get the radicals out of the denominator. Now, think with me here for a minute. What we did when we were dealing with monomial denominators, like if we just had the square root of 7, we would multiply by the square root of 7 over the square root of 7. Here, if we multiply the square root of 7 plus 2, square root of 7 plus square root of 2 over square root of 7 plus square root of 2, we'll have to FOIL these denominators and we'll get a middle term that has a square root of 14, which is even worse than when we started. What we need to do is multiply so that the radicals are gone. And the way we do that is we use the conjugate of the denominator. That's going to be square root 7 minus square root 2. And so the numerator also gets multiplied by square root 7 minus square root 2. Now, in the denominator, we FOIL these out. Now, I'm just going to say here, a plus b times a minus b is always a squared minus b squared. Now, you can do the FOILing if you want, but after a little while, you should see that this fits that pattern. So all you've got to do is square that first number, square the second one, and then subtract them. Now, the numerator, we're going to have to distribute that 15, but let's wait until we've seen if there isn't a factor that'll cancel. So we get 7 minus 2 is actually 5, and notice there's a factor of 5 in 15, and there's a factor of 5 in 5. So we get 3 times the square root of 7 minus the square root of 2, which is 3 square root 7 minus 3 square root 2, and that's as simple as that one gets. So when you have a denominator that's a binomial with radicals in it, you've got to use the conjugate to actually rationalize the denominator, and that does take care of this concept.